I'm going to tell you about a project that we're very enthusiastic about, and I think it can also help the Bitcoin community. It's an enabling technology based on a breakthrough in theoretical computer science that I want to describe to you, especially focusing on the applications to the Bitcoin community. So I'll start with some examples of the things we can do. And let's take some things the way they're done today with Bitcoin and the way we can change it and make it better. So today when a new Bitcoin node fires up, what it does, it downloads all of the blockchain from the Genesis block, and it needs to verify all of the transactions there. If our system is used, which implements succinct computational integrity and privacy, we could do it much more efficiently. The new node that fires up just downloads the last hash, and then it downloads a very short signature that some other node verified all of the blockchain. The signature is short, let's say less than 1 megabyte, it's probably going to be on the order of several kilobytes, and it's very easily verifiable. And the important things are that this is a non-forgeable signature. It cannot be forged in any way, and if you read it and check it, which takes less than 1 second, then you know that all of the transactions were verified by someone, leading to this very last block. Another example of computational integrity. Today, if a mobile application, your cellular, reads a transaction, and it checks it with a bunch of other nodes, and it pretty much has to trust them that they verify that it's legal. Well, if you're going to use our system, then what you can do is you still check that it appears on some other nodes, but you will receive it with a signature that certifies that this node has checked the transaction. And again, the signature is going to be very short, something like 10 kilobytes, easily verifiable, even on a mobile app. And again, there's no way to cheat. Okay? Another example, today, when you want to post a transaction on the network, on the blockchain, you're going to send it to some nodes, and they have to do all of the verification. Again, if someday it's going to be a sort of a complicated script, and it's going to take them a lot of time to verify this. In the new system, if you use SCIP, succinct computational integrity and privacy, then the transaction can come with a signature that basically says the client who's posting this transaction has checked that everything's okay. And now what the node does, it just checks that the signature is okay, which is going to be very, very short and simple to do, and the nodes only need to collect the transactions and just add the proof of work at the end. Okay? And let me give just one example of privacy. Suppose I want to prove to you that I own 1 million Bitcoins. Unfortunately, I don't. But if I were to try to prove to you right now, the simple way to do it is I would point to 1 million unspent coins on the blockchain, and for each one of them, I would provide some information showing that I know the spending key to go with it. Okay? But then, now you know of 1 million coins that at this point in time I have in my possession, and that compromises my privacy or the privacy of my wallet. Well, if you have succinct computational integrity and privacy, here's an alternative solution you'll be able to do. You will provide a signature, I will provide to you, okay, to prove that I have 1 million Bitcoins right now. What I'll do is provide you with a signature that I ran a program. And this program is a very simple one. It went to my wallet, counted the number of unspent coins I had there, verified that they are unspent, sum everything else up. If the number I get is greater than 1 million, I return to you a bit, which is 1. Otherwise, I return to you a bit that is 0. So, all you're getting are two things, a single bit and a signature. The signature is very short, much less than 1 million addresses. And it reveals no information but for the fact that the bit is correct. So you see, we didn't compromise privacy, and yet you have the integrity you need, because the only way for me to produce a signature is to actually know of 1 million unspent coins and prove it to you. Okay, so these are a few examples. And this latter thing is called a zero-knowledge proof in the literature. Okay? And we'll talk more about this in a minute. So the takeaway message is that we have a new enabling technology for Bitcoin. And it is based on rather advanced theoretical computer science and cryptography. In particular, we're showing the first implementation of succinct computational integrity and privacy system, which starts with an arbitrary C program and obtains the asymptotically best possible cost by using a lot of advanced theory that I'll just mention a little bit in the remainder of the talk. So let's take a step back and look at the broad theoretical problem that we solve, of which all these examples are just special cases, and there are many, many more. Basically, whenever you can write a program in C that you would want someone else to run, and you don't trust him, but you want to know that the output is correct, and he doesn't trust you and doesn't want to reveal any information but for the output, that's the problem we solve. So this abstract model has two players, Alice and Bob, and each one has a problem. Alice's problem is that of the lack of trust in Bob, and she wants to have computational integrity. So she starts with a program that she trusts. The program is written in C. And she wants Bob to execute this program on his computer, but her problem is she doesn't trust Bob, so how can she trust the output? That's the computational integrity problem. Bob has a different problem, because Bob is willing to execute the program and even provide the answer. But the computation, as in the case of wallets and many other instances, this computation may require auxiliary information which Bob really does not want to reveal, like his wallet. So Bob is willing to provide the output, but not the auxiliary information. How can he convince Alice that the output is correct without revealing his private information? That's his problem, privacy. Okay? And the third problem is that of succinctness. And that's really a mind-boggling one, because it seems to be nearly impossible. Alice has the program P. She's willing to spend, some time to read the program, to send it to Bob, but Alice might have her computer on a mobile app, okay? So the running time of the program is typically much greater than the program description itself, as in the case of verifying all the transactions since the Genesis block. And Alice is a mobile app, she can't run all of that. So she would like to be sure that the output is correct. But if you're familiar with the undecidability of the halting problem, it basically says that you cannot know anything about a computation without running it and executing it. So let's try to do some logic here. If Alice is going to run in time that's much less than the running time of the program, and she does not trust Bob at all, how could she trust his output? Okay? It seems to be sort of impossible. And that's why the spectacular theory that shows how to solve this problem has gotten so much attention and clout in the world. In particular, for instance, the very latest Turing Award for 2012 is going to Shafi Bolbas and Silvio Micali for their work, for a number of works, one of them, together with Charlie Draco, on the concept of zero-knowledge proofs. Okay? And there are other amazing works about probabilistically checkable and transparent proofs, about computationally sound proofs, and all kinds of efficient versions of them. And that's the part that I've been most active in, which solve all of these three problems in a pretty efficient way. You get computational integrity for Alice. Alice can trust Bob's output. For Bob, he retains his privacy. He reveals no information but for the output. And you do this in a succinct way, which means that Alice does not need to ever execute or run a program that is more than just reading the C code or something like that. And it sounds pretty magical, and it is. When I started doing my research, my advisor back then in the early days was a professor from Hebrew University called Nati Lineal, and he told me that when you deal with a tough problem, there are usually three stages to it. First, you look at it, and then you say, oh, that's easy. After some time, think a bit more about it, and you say, wait, that's completely impossible. And then sometimes comes the third phase, in which you sit for a long time and maybe you solve it. So